My name is Fadil Santos. I'm the director of the IMA. Okay, there we go. Thank you. I'm very pleased to introduce Professor Ingrid Daubechies, who will be lecturing tonight. Professor Daubechies received her PhD in 1980 in physics from the Free University of Brussels. Only 4 years later, she received a very prestigious prize, the Louis M. Pamp Prize in Physics, which was awarded every 5 years to Belgian scientists who on work done before the age of 29. In 1987, she joined AT&T Bell Labs in Murray Hill, New Jersey. It was about that time when she started to become engaged in wavelets. She was a professor at Rutgers for 2 years before settling down to a current position at Princeton University. Actually, I met Ingrid at Rutgers during my sabbatical, and I actually sat on her class on wavelets. It was a very exciting time, a very exciting class. The book, 10 Lectures on Wavelet, on which the class is based, became the best-selling book published by the Society for Industrial and Applied Mathematics. And that book also led her to receiving the American Math Society Steele Prize in 1994. Speaking of awards and recognition, she has received many. Among them is the prestigious Macarthur Fellowship, which is also often referred to in the public press as the Genius Award. It's if you don't know about it, it's a $500,000 award with no strings attached, given to, using their words, talented individuals who have shown extraordinary originality and dedication in their creative pursuits. She was elected member of the National Academy of Science in 1998, and the National Academy also awarded her the prize in mathematics in 2000. The citation reads, "For fundamental discoveries on wavelets and her role in making wavelets methods a practical basic tool." She's also received many international recognitions, including honorary degrees and memberships in science academies abroad. Because of the breadth and of the impact of her work, she's been recognized in other fields, including the IEEE Information Theory Society, which awarded her the Golden Jubilee Award for Technological Innovations. She's also an innovator in education. She teaches a very popular course at Princeton called Math Alive. There's a really lovely webpage about this course. It's a course that takes a non-math major through examples. It teaches them the role mathematics play in their daily life. In the process, the students experience and appreciate the power and beauty of mathematics. So tonight's lecture is going to be on surfing with wavelets. And please give a warm welcome to Professor Daubechies.
Well, thank you very much. It's a pleasure to be here, and I hope we will do a little bit of surfing with wavelets. I mean, surfing over a couple of applications, surfing over a little bit of their mathematical meaning. And I thought, actually last week, I happened to be in Amsterdam in the museum, the Van Gogh Museum. I mean, well, Van Gogh is the way he would have said it. You probably know it as Van Gogh, Vincent van Gogh. Where we were working on a workshop that was bringing together people in image analysis and art historians to show them that image analysis could contribute something to art conservators and art historians. And so I thought I would start our surfing with a slide that I used there. I mean, so this is, on the left, a wavelet transform. And we'll build up slowly the image on the right by using more and more of the information on the left. So let's look at it. And you've started to recognize it. And another neat thing I can do with this is I could use the information that I have at this stage and then separately put the information that I still need to add to it to get the full thing. So let's look at that. That's these two things. So you have decomposed it into something that gives you the subject and something that gives you all the fine details. And that was just to give you an idea of things we can do with wavelets. I mean, I'd like to explain now a little bit how we can do that. So for that, I'll switch to a different talk. Oh, shoot. That's not what I wanted to do. The resolution is I have to drag things from over there. My screen goes to here, you see. And so, okay, back to the start. And let me give you a little, oh shoot, video mute. Is this it? Yes, fine. So let me explain to you a little bit about how a wavelet transform can work. So basically, I mean, we had these images. Images consist of pixels. Pixels are little squares that have a certain, if you look at black and white, certain gray level. Gray levels typically go from 0 to 255, from completely black to completely white. If you have color, then you have the same thing in red, green, and blue. But so we have different numbers for these different pixels. So an image, from a mathematical point of view, as if you want to do image analysis, is just an enormous field of numbers arranged on a square array. Okay, so let's take one line out of the image. Then I just have one line of pixels. So one line of numbers. And as mathematicians, as soon as we get something, we like to make graphs of it. So I can make a graph of it, and I can imagine, typically an image looks a lot like this, and then it has sudden, and then it has stuff like this, and then things like this, and so on. So this would be a sudden transition from something very light to something much darker. Well, you can imagine, this is not a natural scene here, but you can imagine taking a snapshot here, and you would definitely get places where sharp lines, sharp transitions exist between darker and lighter. And you have regions where shading, I mean, on the screen you see it nicely. I mean, you go from light to slightly darker. So you have shading that slowly happens. You can have things that are oscillating, like the wall there, or like the ceiling there would actually have oscillations that look more like this. And you can have also a sudden line. I mean, this black line here at the edge of the screen would actually occur like a line like this, because it's a dark line and low numbers are black. In any case, we have something that you can sketch as a function, a graph of a function with smooth and sudden variations. Now, okay, if we blow this up because we know that we are discrete, what we're really plotting here are just levels. I mean, let's give a certain width to the pixel, and let's imagine that we have a piecewise, that we have the constant level in each pixel. So, I mean, of course, this goes on from there to there in order to describe my simple image, one line out of my simple image. But I'm going to view this in a kind of hierarchical way. I want to distinguish, just like we saw in the image that I gave at the start, we were seeing overall features, and then we were zooming more and more on detail. So we peeled it apart into very fine detail, coarser detail, and so on. So let me show you a very, very simple way of doing that. What I'm going to do is I'm going to group these pixels in groups of two every time, and I'm going to compute for each of the two their average. I mean, can't be harder than that. I mean, I once had to explain this to somebody who was doing a little interview for a local public television. And he says, "Oh my God, mathematics." I mean, I said, "Well, come on." He says, "An average." I said, "Yes." He says, "Averages he could still do." Okay, so we're taking averages. Now, if I then look at I mean, so I'm going to replace the original black thing by these averages, which are twice as wide. And of course, I've made a mistake. I mean, the original levels were not at those averages. And what is the mistake I've made? Well, I had to go a bit lower here and a little higher. So that's this mistake. And then here, I have a tiny little mistake. So a tiny little bit lower, a tiny little bit higher, and so on. And so you see that for every little block, I have a kind of up and down oscillation. And at some later point where I'm going down in the other direction, for instance, if I blow this up, I will have something like this. Then if I start to compute averages there, horizontally, then of course the mistake I've made will be an up and down, but now in a different direction. So all these, what I've done, when I replace the original fine scale with all its richness of detail by this green superpixels, if you want, is something that I can depict completely by just taking this kind of elementary building block. I mean, and I'm drawing this for facility. It's really something that's 0 here, 1 here, then -1 here, and 0 again with little dots here. The vertical lines are not in the graph. I take this, I make it very, very narrow, because remember, I'm at a very tiny scale. I give it the right amplitude. I have different weights for it here, or there, and I put them in the appropriate spots. But so this one building block, and I make it negative if I need to, like here, and sometimes it's positive, like here. So this one building block suffices to express completely the difference between the original and this green coarser version. Okay, so that's my fine scale detail, and in these tiny little Lego blocks, these up and down things. Now, there's nothing that prevents me from continuing. I mean, after I've decomposed my original. I had an original, and I decompose it into averages and fine detail. And then what I can do is I can put the fine detail on the side. That's one layer. But the averages are going to look exactly like my original thing did, except at a coarser scale. So I can just repeat the whole argument there. I can repeat the whole construction and take averages of them in groups of 2. And again, look at the differences. The difference here that I've made is something that looks like this, and so on. And again, I see that I have layers, but now of things that are twice as wide. And so once you see this happening, you can imagine yourself, I mean, I always have this mental picture of peeling off layers of an onion. I mean, you peel off a layer of detail, and then more detail, and so on. Layer after layer after layer. And that's what was happening in the example that I gave you. There's one difference. I mean, here I'm talking about lines. And pictures, of course, are not lines. They're two-dimensional. So, well, we'll have to do it in 2 dimensions. Let's imagine doing it in 2 dimensions. So I start with my picture. My picture is big like that. And it has a whole lot of rows and columns. And then what in each row of let's say, 1024 pixels, I can split into half of that number in averages and half that number in differences. And I do that for each row, and I put all the rows below each other. And so what I will get is something that has not been treated vertically, but it has been treated horizontally. And so I represent that in this way by still being black here, but okay. Now I have, horizontally, I've peeled off coarse things from detail. I can do the same thing vertically. And if I do that, then I will have, I mean, here I have to represent it in averages and differences. And I have to do the same on the other columns. So again, I get averages and differences. And so now you see that I have 4 blocks in all. Blocks that came from horizontal averaging and then averaging or differencing vertically, and blocks that came from horizontal differencing, and so on. And so what we do is we shove these 4 together, and that gives you, and that's actually an explanation of what you saw in on the poster. I mean, let me turn off this light for a moment. And I've been coached in this, you see, I mean, but maybe not well enough. Okay, so, lamp. I'm hitting lamp. says wait. We're waiting. Okay. So, is that focused? Okay. So, on the poster, you had, this was actually one big picture that had been decomposed into 3 layers. And here at the top, you had the averages both direction. This is this weird, funky building across from the IMA. I mean, it's all in metal. And is it a Gary building? It looks like a Gary building. It's a Gary building. I mean, we have our own, so it's also weird. And so we have, and what you see is these are the 3 different images. You see that here, horizontal lines stand out. And why do they stand out? Because horizontal lines are things that you see when you make a vertical differencing. I mean, and a horizontal averaging will say, oh, yeah, it looks the same, I don't care. But when you make a vertical differencing, it says, oops, there's a change here. Something is happening. And so if I look back at what I had drawn here, I think we may be, so this is a vertical differencing and a horizontal averaging. Then if you difference in the other direction, so I make horizontal differencing and vertical averaging. Horizontal differencing in this direction is going to give me a big number, a big says, oops, something is happening when I go from very dark to very white there. So when I have a vertical line, a vertical transition will show up in horizontal differencing. And indeed, you see that vertical features stand out. And then, well, here you have diagonal features mostly that stand out because you've differenced in both directions. So that's an explanation of that poster. So let's go back to here. Okay, I don't know how to, I want to go back to black screen. That's what I tried. Okay. I'll have to come back and show that I can do better next time. Okay, so this is the explanation. But then, of course, just like we were doing in the 1 dimension, we're not going to stop. Now that we have got a nice principle, we have here something that looks like the image but smaller. Why stop there? We can do it again. And so when we do it again, we'll, on that green image, we'll do something where we do our differencing and averaging on that small one, and that gives even smaller arrays. And the other ones we keep. So the other ones we just put around it, and so on. I mean, so here all the, and so on. And of course, I will keep going like this as long as I am patient. I have the patience to do it. And so we can replace this again and so on. And that's what I was doing in this Van Gogh example. In the Van Gogh example, I was showing you that, I was going from 5 levels down, and I was building it up gradually. And as I was building up gradually, what I was doing was I was building up first from only that information. I mean, I can go back from there. I could say, look, suppose that all these other things had given me nothing. There was no difference. There was no fine detail. Then you blow it up again, and you get something very, very fuzzy. And then you add a detail, and you add a detail. So I can do that, and that's what I was showing you. So let me show you another example. Okay. Here, it's a little less appealing maybe than the Van Gogh picture. We have a boat. This is just to show you that it doesn't have to be square. This is if I average in both directions. And here are the 3 difference images. The convention here is slightly different from what you saw on the poster image. Here, because I was also wanting to show positive and negative. You see, if you take the difference, the original gray levels are black and white, are gray levels. They're all positive. If you take differences of 2 positive numbers, you can end up with a positive or a negative number. And so gray in the difference images stands for 0. And black stands for very large and negative, and white for very large and positive, except the white doesn't show, but I mean, very well. But so you see that you have horizontal lines standing out where we have done the vertical differencing on the lower left, and vertical lines standing out where we did the horizontal differencing. And I can go further. I mean, for the average thing, I can do the decomposition again, and I have to keep all the other information. I can, on that smaller average, do it again. and add all the other information. And again, and add all the, and again, yes. Okay, I think that's it, yes. Okay, so now we're going to do the reconstruction here that we had seen with the Van Gogh picture. So I'm taking only the thing in that little top left square and reconstruct, and I'm adding in the detail. Okay. So we're going to look at that again. Going to look at that again at we're going to concentrate on two pieces of the picture. One is in the sky and the other is in the sail. And we'll see the originals on the left and on the right. We see now the very, very coarse approximations. And I'll go through it twice. First time, I'd like you to concentrate on the sky and see from when on you consider that the sky is already good. Probably people at the back consider it good already now. People at the front probably find it a bit washed out. But the sail, everybody agrees, is not there yet. So I'm adding detail, more detail. Even from this close, I couldn't say at the last transition whether the sail improved. I mean, so I don't expect that you could. But, okay. So the sail was ready much sooner than the sail was ready much later than the sky was. So let's see why that is. Well, first, I have to confess you something. The differencing and averaging that I was doing before is really morally what happens. But in practice, we are a little bit smarter than that. We do something a little bit smarter because, you see, what we want is the detail to capture detail, interesting stuff. And if I just did averaging and differencing, then indeed, if there was nothing happening, if all my pixels, if all my numbers were the same, then indeed I didn't have to add detail. Taking the average of this, if I have little pixels that do things like this, or I replace them by their averages, I mean, is exactly the same. So the difference is going to be 0. But if I have something where the pixels just become, where I was constant becoming lighter, I mean, so just a linear progression of light, then I will have a similar linear progression of light in my averages, but I have made mistakes. I have to constantly adjust now to, I made a mistake. I was a little bit too high here and a little bit too low, and so I mean, my differences will look like that. And you say, well, that's how you define the game. Well, but I'd like to define the game so that if a piece of my image is so boring that I could describe it with just 2 words on the telephone, that I don't waste mathematics on it when I try to decompose it. So, I mean, I don't want to have all these coefficients here. So what that means is that I have to find a smarter way of computing averages and differencing. And there are ways of doing that. What you can do is you can just say, look, I mean, what this is helping me to do is, from the green stuff, predict what the black stuff would have been if I had kept all the information. Well, there are smarter ways of predicting. I can predict in a way by saying, look, if I have green stuff like that and it processes nicely, it progresses in a nice way, then I would predict things halfway in between and I would get the black stuff. So we do fancier averaging and differencing than what I showed you. What it really does is it will do perfectly as long as you have a low-order polynomial. So I had constant linears. Typically, you try to use schemes that will do well up to cubics or so. So as long as things behave in a nicely predictable way, the details are not needed. The averages already take that into account. So that's one thing. And then a consequence of that is that when I start decomposing, suppose I have a very sudden transition, or I have something that has a cusp, or I have something that's very smooth. Then what happens is, and you have nice mathematical theorems to actually prove that you see here, I mean, regardless what the average is going to be, it's going to be very hard to predict that I'm going to have a sudden transition. I mean, so you will have to pay for this. In order to really reconstruct this well, you will need wavelet coefficients that if you go to finer and finer scales, that will, they will not decay. They will remain large. The amplitudes of the differences will remain large. If I go at a place where I have here, so now I use the color to indicate different regions, not differences or averages anymore. So in this region, where the function is continuous, so at least it's not going all of a sudden from white to black. But it was nicely increasing, and then all of a sudden it reverses itself completely. That is something that stands out, like a ridge, like a fold. If you have pages of a book and they fold, the way you see that fold, that darker fold in between is exactly something like this, except in reverse. But so this will also need fine scales, but not quite as bad as before. So the finer scales, I will go down quicker than there. And in places where I'm really nice and smooth, you see, if I do something like this, a third-order polynomial catches that perfectly. That means that my details at fine scales will just be 0. So in a region like this, I will find that my wavelet coefficients, as I go to finer scales, I just don't need them at all. So what that means is that, of course, in practice, you don't keep numbers. Depending on the application, you may not keep numbers that are smaller than, let's say, 1,000th for images, for instance, or than 10 to the minus 6 if you want to do computation, or 10 to the minus 20 if you want to do incredibly accurate computation, or to want to show off to other numerical analysts. So we will put a cutoff, and meaning that below that number we don't need to keep things, and that will tell us the finest scale at which we need to go in order to see something. And you see here I need almost nothing at all. Here I need some scales, and here I need all the scales. And that's what was happening let's see again. So I was very smooth, and as I go smooth, so I go down, and you see in the sky I had not much detail, so I wasn't necessary. Oh, sorry, sorry. We'll go back. You'll show it again. I'll show you again what I saw here. So we have in the sky where it's very smooth, you see not much detail. The detail coefficients are very small. I don't need them. In the sail, where things are not smooth at all, especially around the letters, I need all the detail in order to make that really sharp. Okay, now we've seen these compression slides a couple of times, so let's go talk about compression. So you can use this for compression, of course, because what it means is that I'm not going to waste energy on storing those details. Places where detail is 0, I can forget about it. Now, that is, so if I have this boat image, and on the right a transform, I could take things that are just above a certain threshold, stuff that I've painted red on the right, and that means that I have retained about 1/30th of the original information, and I still get reconstruction on the left. Now, it's not perfect, so I'll toggle back and forth between the original, and this is original, this is, so, original. You see, it's not perfect, especially in the numbers, you saw a difference. But it's pretty good. If you consider that in the original picture, I had 8 bits of information for every pixel to give you the complete gray level. I've now reduced to about 1/32 of that information. That means that I have just about, if I hadn't been clever, enough information to tell you for 4 of those pixels whether it was black or white. Yet, if by being clever, I can get the image to this precision. Okay, if I do a little bit more, then you have the image almost perfectly. So this can be used for compression, is used for compression. The JPEG 2000 standard uses wavelets for compression, actually uses the smarter scheme that I have been used to make these pictures. It can also be used for many other things. We have our detail that is very, very tiny at fine scales. And as we go to coarser scales, it becomes bigger and bigger and bigger. But that means that if you want to thumb quickly through an archive of images, and only look at coarse scales, and then say, oh, this image, I want, and I don't even need the whole image, I just need this little bit of the image, you can very fast and retrieve that little bit of information. I mean, you can imagine it for things like, typically this kind of technology is used for things like Google Earth applications and so on, where you have an enormous data set and you want to retrieve only pieces of it. And you can do this in an interactive way. So this illustrated here on this boat image by the fact that I identify on this very coarse image that the region of the sail where the number will be, and I tell this to my data structure. So I paint ahead of time. I tell them where to find the addresses of the region I want more of, and I've painted those in red on the right, and I'm only going to use those. I'm not calling back any others, and this is what I reconstruct. And so I can do part of it very sharply and not waste any energy on the rest. Applications. The very first application in which the wavelet compression was used was a standard for fingerprint compression by the FBI. This was in the early 90s. The FBI at that time went over to digitization of their fingerprint collection. And they have, of course, an enormous collection of fingerprints, not only of criminals and suspects, but also of every single person who immigrated to this country. I mean, one of the things you have to do is you have to get fingerprinted, as all of you who came as an immigrant must remember. They had, I mean, the way they had at that point, so early 90s, they had still everything on paper, so on cards. I mean, you know these cards on which they roll your and so on, and then very dirty ink, and then you have to wash your hands and so on. But so they do this, and they put it on cards, and they had all these cards for everybody. And the way it worked is that they had 20 cards per folder, and so many folders per drawer, and so many drawers per cabinet, and so many cabinets, and so on. And this was, the number of fingerprints they had was, they could express in acreage. I mean, just of cabinets next to each other. So they had an enormous collection. And they wanted to digitize it, and they wanted to compress it once they were at it. And they wanted to compress it in such a way that after they decompressed it, they could still, with high reliability, recognize whether two fingerprints were of the same person or not, with the same reliability as they could originally. So they had a very pragmatic way of expressing how good compression had to be. And so what they did is they wrote out a competition, and they asked different teams to participate, and different universities and industrial labs proposed algorithms to do this. And it was important for them that this could be done with an algorithm that was very simple, so that it could be manufactured very simply and cheaply. Well, because they weren't really interested in only the most prosperous precincts being able to acquire this gadget and send their fingerprints. They wanted a cheap thing that everybody could buy easily and an easy standard. And what happened is that this competition was won by something that was proposed by a team in which Los Alamos participated. And the standard was written by Chris Brislan at Los Alamos, who let me use the pictures that he used for that meeting. And what did win was a Wavelet proposal. So here are, these are pictures from that time. So here is an original fingerprint, and a Wavelet reconstruction of that fingerprint with a compression ratio of about 18, which is what I wanted. Now, you don't see much difference, but that's really not fair, because, it's not fair that I ask you to look at a difference, because fingerprint experts look much closer. So here have another fingerprint of which I have actually large blow-ups. And this blow-up shows interesting features. It shows, of course, that we have these ridges on these fingerprints, but also that there are other things that are of interest. You have these little islands between fingerprints. You have ridges coming together, splitting up again. And you have, on the ridges themselves, you have these little whiter spots, which are sweat pores. So these are all features of our fingerprints that all really matter in order to identify fingerprints. So fingerprints are identical if not only if those ridges correspond, but also the islands and so on. So it was important in recognizing fingerprints not only to get the bigger features, but also very fine scale features. So whenever you are interested in fine scales that are very local and bigger scales that are much less local, wavelets are a good idea. And so that's why wavelets did work very well. So here on the right, you see that original compressed with a wavelet compression of about factor 15. And here is what, okay, so we have a factor 19 now on the right. And on the left is what you would have had as compression with then the JPEG standard that was then in use. In the meantime, JPEG standards have been able to do better as well, but still not as good as wavelets at the many different scales. And that's why JPEG 2000 uses wavelets. So, but you see that on the left, you have these islands much less recognizable than on the right. So this is how wavelets made it into the fingerprint standard. Now, let's go back to Van Gogh. And because I'd like to show you I'd like to show you that presentation. And I thought I would show you the slides in the language of Van Gogh. Actually, so I'll explain them in English, of course. So I'll give you, which happens to be my mother tongue as well. So that's why, which is Dutch. So what happened was that the Van Gogh Museum had given us a number of challenges. Because, I mean, we didn't expect anything really concretely useful to come out of the workshop. But they wanted to have our attention focused on a couple of things. And the whole goal of the workshops was actually to start getting conservators and art historians interested enough in the image analysis know-how that teams would be formed where people in image analysis and art history would work together. Because it's only by working with people who really have the domain knowledge that you can do interesting stuff. Otherwise, I mean, you go away, you do something, and they say, yeah, but that's not really, what can I do with that? I mean, you have to really be involved with each other, which is something that most applied mathematicians know. I mean, there's a time for doing your math on the side, but there's a lot of time that you have to work with the people who know what they want. Because the one thing when they explain their problem to you is that they don't, it's not mischievous. It's not because there's bad faith, but they don't explain you everything because they don't think of explaining you the things that people in their field have learned since kindergarten. I mean, they know this. I mean, so typically the way collaboration works is that they explain things to you and you make a first model, and you don't try to do too much because you know at that stage it's not going to be good. And you go back and you say, is this what you meant to say? No! I mean, because, and then you say, but you didn't tell us that, but everybody knows that. Okay, so you go back. And so after a couple of these times, you understand better, and then you can start really working together and refining the thing. But so we were at that earlier stage. But then, anyway, had given us a challenge. They had given us a whole number of paintings that were by Van Gogh, and some of which are quite atypical. Like, I mean, I don't know that many of you would have recognized that little nude model on the left, and or that Japanese-inspired painting, second from the left at the bottom, as Van Gogh's. But I mean, he painted many more than only the very celebrated paintings. And they also gave us paintings that were by contemporaries, friends of his, or the lady with the black bonnet is actually somebody who was, in a certain sense, a disciple of him, a younger guy with whom he talked a lot in the final 2-3 years of his life. And at the right are paintings that at some point were attributed to Van Gogh. Some of these are paintings where they just made a mistake because, well, they were in his possession when he died, but they were just swaps he had made with friends. I mean, sometimes painters among friends, they say, oh, I like that one. Oh, and I like this one. Oh, do you want to share? And so he had paintings by others that were not by himself. Some of them, like the flower painting, is by Monticelli, who was an inspiration for him when he was very young. And so some of his early paintings look like these Monticellis. And then the one on the bottom left of the group, so the group on the right are the ones that are not Van Gogh. The one on the left bottom is a Wacker forgery. This is a forgery from the 1930s. Somebody in Germany who was an art dealer, a very distinguished art dealer, who found a number of fantastic Van Goghs, which later turned out to be, well, found not quite an orthodox way. So they were all fakes. But at the time, they really did fool the experts. And so they wanted to ask us, can you see a difference between Van Gogh's style and other people's style? Can you see a difference between forgeries and true paintings, which are two different questions? And so what we did is we looked at a wavelet decomposition of the paintings. And so here we have what we started with, a decomposition into wavelets of the bedroom painting, and how we get details at some scale and coarse stuff at the other scale, and how they are ideal to analyze the brushstroke technique of the painter. So here I've taken a very, very small detail, and we look at the wavelet decomposition of that, and you see that you start seeing in the wavelet decomposition, you start seeing a graininess that will tell you more about the brushstrokes. In fact, we used not just the horizontal, vertical, vertical, and vertical, horizontal distinction. We used a more finely tuned direction thing, partly because we wanted to distinguish. You see, if I take the horizontal and vertical differencing that I did earlier, then diagonals like this are not distinguished from diagonals like that. And, I mean, that's not a good idea. I mean, they are. So we wanted to distinguish these directions, and so we used directional wavelets. And so here, let's look at the reconstruction here for a little piece of that self-portrait. And you see how I build it up gradually. We could then, having done this with all the paintings and analyzed them mathematically and so on, we could then try to see what features there were in Van Gogh paintings that were typical for Van Gogh and less typical for others. So what type of things? So what we did actually, we analyzed how much detail occurred at different layers, and we also analyzed locally a kind of hierarchy of detail. You see, if you have an edge, then you're going to see it at many different scales. We saw that earlier, because you have all these fine scale, these coarse to fine scale wavelet coefficients. When there's just unevenness, you see that at fine scales, but it's washed out at coarse scales. So you can look at these hierarchies through scale. And what we found was that in Van Gogh, there were two transitions that were very, very characteristic for many of his paintings, at an angle of 75 degrees and at an angle of minus 15 degrees. And in order to express that, what I've done is in a piece of the painting that had these features, I'm going to enhance them. And so I'll toggle again back and forth so that we can. So here, in just a little piece on the left, I enhance in the mustache things at 75 degrees. And then on the face and on the nose and the cheek, we enhance something at minus 15 degrees. So what I've done here is picked the exact scale at which we found that this hierarchical feature was important in Van Gogh and not in others. So let's toggle up again. I'll go back and forth a bit so that you can try. As it blinks to you, you can see what it means. And this was something the art historians were interested in. Say, oh, wow, never thought of that. So, I mean, I guess later they were looking at 75 and minus 15 angles. So this was a way of expressing this, that we actually have the scales at which their significance emerges. And then, well, we had to compare all these paintings. So we had a good way of describing Van Gogh's style compared with the style of other painters by these features that stood out. But we still had no good way of detecting forgeries, and which we then realized was a very different thing. And we decided we wanted to see whether we could decide on a distance between paintings. And to do that, I mean, the data were given us by the Van Gogh Museum in an incredibly fine resolution. I mean, we had to laugh because they gave them to us in black and white because, well, they didn't know us at the beginning. So museums are very, very careful with their high-resolution reproductions because it's, in a sense, their intellectual property. You can print high-quality and very expensive art books if you have that. And they don't really like to have competition for their own artworks. So they gave us Van Gogh in black and white, thinking, rightly I think, that nobody would be interested in printing a high-quality, expensive art book on Van Gogh in black and white. So, but they gave us thumbprints in color. Now the thumbprints were, by my standards, very high-resolution color images. The black and white, of course, had a resolution that was 10 times linearly higher, horizontally and vertically. So there was no way we could treat these as a whole. So we actually had to cut the little image, the different pictures into patches, and we would then treat each patch as an image on itself, and we would compare patches of one painting with all the patches of another painting, and then start with the second patch and compare, and so on. And so that way, we actually we synthesized this, and we computed a distance between paintings. So distance between the patches, and we added all the distances pairwise for the patches. So we could define a similarity between paintings, I mean, which was only capturing one part, of course, of the whole thing. And then we had this similarity. If you have a lot of distances, you can try to make an arrangement in 3 space that visualizes that is most faithful to what you have found. And we thought about making a little model, I mean, one of these montages that we would rotate, but it was way too much work. So we made a little movie that actually showed that 3D model. And so I'll try to see whether I've understood how I should do that. So let's look at that movie. Oh no. Where is it? Ah, here. So is it coming? It came when we tried it out earlier. Oh no. Oh, sorry. I have this beautiful movie here. And, okay, so what happened is that, why is it not doing it now? Shoot. Okay, I'll try once more, and then, it is? No. Who was? I see. Well, I'm not. It did it beautifully before. I started again, but I tried starting it again before. I mean, okay, I'll start it from scratch again. Okay. Oh shoot, that was not helpful. The problem is, you see that part of this thing, this screen is not on my, it's here, and I can't reach it with my mouse. Oh, maybe I can move it. No. Ah. This is weird. Okay, I'm sorry, I give up. So, but I can describe to you with my hands. So what happened, so we had it's like a little mobile of all these paintings, these little paintings hanging there, and we put a red dot on the paintings that were not by Van Gogh. And if we used one feature in order to distinguish the different characteristics, we found that Van Gogh paintings had mostly moved outward, but crucially, the Wacker painting had not. I mean, it was still fairly close to the center, and that's the one that they really wanted, because the other ones were mistakes that with documentation they realized, but that was the one big forgery. I mean, you really want those to distinguish those. And then if you use two features, so the transition's not at 75 and only, but also at 15 degrees, the Wacker was already moving much more outwards. And then later we realized that, in fact, we could distinguish, and this is a story with which I will end, because it has some, it has a little tail that stretched into this here. So this first workshop at Van Gogh we have had two workshops, and the first one was last year in May. And we wanted to distinguish copies from originals. And we were even challenged. I mean, the NOVA, television program NOVA, had heard about this, and they wanted to make some television out of this. So they actually found an art restoration expert and asked her to paint a copy of a Van Gogh, a very little known Van Gogh. And they then gave us, 3 days before the workshop, they gave us scans of 5 authentic paintings by Van Gogh that we hadn't known yet, and this one copy. And they challenged us, could we get out the copy? And that's when we realized that the style analysis was not sufficient, because they were all of the same style and we could not distinguish them, and we were in a panic. But then we thought about it and we said, look, what do we expect to be a problem with somebody who copies another painting, who doesn't paint in their own style? We expect that it's slower, more hesitant, that you look more. And of course, this is an expert who does it, so we wouldn't look at it, we wouldn't see that with the naked eye, and certainly lay people like ourselves wouldn't see it. But maybe you can see that if you look finely enough. And so we decided to look at very, very, very fine scales and look at whether there was more fine scale information in the copies in one painting than in all the others. And lo and behold, it stood out. It just shone. When you looked at fine scales, it was a peak among the other paintings. So we had, there were 3 teams that participated last year, and we all 3 identified, and we were all very happy about this. And we have, if you go to the NOVA website and you search for it, you have a little video there of the program and showing how happy we were when we found out. And now, I said it has a little tail because, well, we were scientists. We are scientists after all, and when we explained this to art historians, they said, come on, you can't tell me that you can detect this. It depends on the background, it depends on the fluidity of the paint, it depends on so many things. There's no way you could see it. We said, okay, so we have to, maybe they're right, and maybe we should validate this. So what we actually did is we invited that art restorer person to come to Princeton for 2 weeks, and she painted for us a whole lot of little paintings herself fluidly in her own style, and then painted copies of her own paintings. So she actually walked around my house and she found all kinds of little tchotchkes, knickknacks, and so on. And so I now have a lot of paintings of my knickknacks. So she painted little paintings like that because it was only 2 weeks and she needed to make something like 20 paintings. So she made little paintings, and then after she'd done the original painting would take her something like 20 minutes or so. She would put aside the subject and she would just copy the painting. And we were putting ourselves in the most difficult situation because we were having a copy made by the person who'd painted the original, hours after she'd made the original. And so we felt if we could detect it there, then people would not be able to say much. To have the same objections anymore. And we thought we might because we actually observed, and we hadn't realized, but she said she had expected that to paint an original one would take her 20 minutes. Well, to make a copy of the one she had painted in the morning, copy in the afternoon, would take her something like an hour and a half. It would take her much longer to brushstroke by brushstroke try to copy exactly what she'd done in the morning. So we found many things. Apart from that, the Van Gogh Museum, intrigued by what we had done last year, had also given us a new data set in which they gave us some Van Gogh originals and a copy that had been painted and that they like a lot because it had been painted by a contemporary of Van Gogh, by an art collector, shortly after his death, who liked one of the paintings very much. And but this art collector, being more wealthy than Van Gogh, was able to afford better quality of paint. In particular, the red that Van Gogh used is red that has faded by now in many of the paintings, because red is a color, if you want to buy a stable red, it's expensive. And so in the copy, they have much more of the red preserved, because this man could buy better red than Van Gogh could. And so they liked this painting, and that's why they had it, a negative of it as well, and so on. And so that was scanned in, and they asked us, could we distinguish that this was a copy? We didn't have the original, but we had originals that Van Gogh painted around the same time. And when we tried their first challenge, we were in bad shock, because we couldn't. We said, what's going on? And then we looked in more detail, and we realized what we hadn't realized before, that in the data set they'd given us, the quality of the data was very, very uneven. I mean, some of these pictures, these high-resolution pictures, were much sharper than others because they had been scanned in. Of course, they didn't scan them in from the painting. You don't take the painting and slam it on I mean, they had very high-resolution photographs, and they scanned those. And those photographs were very high-resolution. But since we were interested in resolution that went way beyond what the art historians typically went, they didn't care that the things were not always as much in focus. I mean, that they were all of an equal focus, because this went beyond what they needed. To them, they were all equal focus, but not to us. And so we realized that depending on when those pictures had been taken, and also which museum, Kollermuller was much sharper than Amsterdam, we found, that affected the data. And because the forgeries or the copies had been much less in demand, these pictures had been taken much more recently, and they were higher quality pictures photographically, and so we had more fine details. So all this fine detail that stood out before, we thought, oh my God, and this was on television, and we went public about this, and this is terrible. So we were really, really glad when we realized this, that we had the data set painted by the art restorer, because we would be able to really check. We had ground truth there. And it turned out that indeed, but we had to do a much more detailed analysis than the one we had been so happy about on NOVA last year, that our intuition was right. We can indeed, for most media, not for all, because she did it with acrylics and with oils on very absorbing ground and non-absorbing ground and so on. In most of these circumstances, we could indeed detect which was a copy and not in a reliable way, but it was a more detailed analysis. And we were very happy we'd done that, because otherwise we would have been, as we say in Dutch, we would have stood in Amsterdam with our mouth full of teeth, met onze mond vol tanden, which means having nothing to say. I mean, but so I think my time is up, and I'll stop here with the surfed over words.
Professor Daubechies would be able to answer a few questions if you have any.
Any questions?
Are there any questions?
Oh, it's going to be hard. Yes, here's a question. Okay, so the question is, did we look at I mean, when forgeries are made, they're often not just copies of a painting. They're done in the style of somebody, but they're not a copy. So if it's not exactly a copy, but somebody who tries to mimic a style, could we detect that? In fact, the Walker picture is one of those. I mean, they're not exact copies, but what they did is they took seeds, because when Walker very often, if you like the seed, we paint several versions of it, slightly different. So they took something that existed and painted in a slightly different version. So, and they did have that. But I predict that if somebody first practiced 3 years not painting in any other style than the style he wants to imitate, and then paints a forgery, we would not be able to detect that with these technical methods. So it's not to say that you now have to go practice Van Goghs for 3 years in your painting. But I mean, there's much more than technical methods, of course. I mean, we at no point did we want to say that we wanted to take the place of art historians. We were very careful with that, especially on television, because the interviewer was constantly asking us, so do you think that machines will replace this one? And when you say no, I mean, so that we couldn't cut it out or so, because I didn't want to sound out of that, because that was not our goal, and we did not want to portray ourselves.
Other questions?
Yes.
Have you looked at combining left and right eye images into one?
Okay, so the question is, have we looked at combining left and right images, eye images into one data set? And I haven't, and but I know this has been done in the image analysis, in the vision community. And in fact, Stéphane Malat, when he started work on Wavelets, that was one of his earliest topics, to combine left and right images. But for paintings, it doesn't make much sense. Other questions? Yes? Yes. Okay, so the question is, for the black and white analysis, for the brushstroke analysis we did it with black and white, did we also do things with color? This year, actually, for this year's workshop, we were given color information only for half of the paper, and every time. And so we did analysis in color, and we of course did find a richer structure. But we found that actually we are now at the stage, we didn't make this year's workshop so much more progress over the last years, except by a better understanding of the data set and so on. We really feel that we are at the stage where we have to work with the people who know the domain before we can make better progress in that. And that's going to happen now. So we have planned another workshop 18 months from now. In the meantime, every team of image analysis is going to hook up with art historians who have declared their willingness to do this. That's where we wanted to get. I mean, because before that, we weren't there. Now we have that, and now we can get further. Yes?
It's useful for now an authentic photograph or some post-processing.
Okay, so the question is. Okay, so the question is, can techniques like this be used to distinguish an authentic photograph from a processed photograph, for instance, for cryptanalysis? So,
Evidence.
Or evidence in a, okay. So there are many questions in that one question. You can definitely use multi-resolution techniques as one of the tools in image analysis to use it for forensic purposes. In order to see whether an image has been processed, whether something has been inserted into another image or not, I don't really know how that works in detail in practice. I have once talked to somebody who said that the basic principle was that if you could take it out easily, then it had been put in. I mean, normally to get something removed from an image isn't easy. I mean, and if you find something that you can remove really easily, then it's kind of suspicious. But image analysis techniques have been used in several instances as in forensic evidence in trials. For instance, it's possible, and you can do that with wavelets, but I mean, I think that one time that it was used in trials, it was not done via wavelets, it was done via partial differential equations. What you can do is have several images taken of very, very blurry scenes. I mean, for instance, a nice example that you can find on the web is a car driving out of a parking lot, and everything is blurred. But because you have a number of blurry images, you can nevertheless reconstruct the license plate with very, very high accuracy. Because you have different blurry takes of the same thing. It gives you much more information than you might think. And I have actually a collaborator of mine actually did work on pieces of fresco where only pieces are known and a black and white picture is known of the fresco before it was destroyed. So the piece of color, and they can help propagate color in the environment. So you can do many, many things. But typically, I mean, what happens in these things is that you use a whole lot of different pieces of mathematics. You don't use only the little wavelet surface that we've done. You can put in other things, variational principles. All the tools that you can bring to bear together. But yes. Yes.
Do they use wavelets at all for, say, like audio signal processing, like compression into MP3s?
Okay, so the question is, are wavelets used for audio signal processing, like compression MP3s? No. In audio, what is used for high quality audio, they use filters. So they do use, I mean, taking it apart into different bands of information. But those bands have been, have been over the years specifically designed exactly for that purpose, and they're very finely tuned already to the ear. In audio, it is less important be as localized in time, because after all you sample well, you sample at a very high frequency for high quality audio, 44,000 times per second, and so their filters are much longer, and so they can afford to do much. I mean, here we were filters that were used in all the image analysis I was showing you were, I mean, instead of, if I took an average, I used 2 things. So I'm using more than 2, but I've never used more than 9 altogether. So it's very, very short. In audio, you use much longer things. Plus, audio is very, I mean, what they use is knowledge about where they can make more mistakes than others. Masking of error masking, which is quite complex, and I mean, I don't know much about it. I know that it exists. I've talked with people who I mean, at Bell Labs, when I was at Bell Labs, and the next corridor over, there were people working on this high quality audio, and it was amazing. I mean, they would play these high quality recordings of high quality systems, and they would hear things. I mean, you say, oh, there's an artifact there. I haven't heard anything. I heard perfect sound. I mean, they have an incredible ears. Yes? Okay, so again, the question was, can the analysis be done on watercolor painting where the brush stroke isn't as visible? Well, I guess that what we would do, we would find is different features out of it. I mean, in watercolor, what you do have is this nice sharp edges at where the drying started of a brush stroke. I expect that would have information. We haven't done watercolors, but I don't see why there wouldn't be any information. Yes?
Are all of these applications which are active now still using your Daubechies Wavelet as the principal wavelet?
Well, I never call it that anyway. But the JPEG 2000 standard uses wavelets that were first published in a paper by 2 co-authors and myself. The applications which are not orthogonal, which are biorthogonal. The orthogonal wavelets, if you come back, if they're very short, they often use wavelets that I first published. But I mean, what people should, I mean, if people have an application and they know the application well, then we know how they should use what they know about the application to design the best way for that application. I think that's what they should do.
I think we should thank Daubechies again for a very inspiring talk. Thank you very much. And we have extra cards from the lecture. If you'd like to come and get one, please come down here.